This is the malware analysis project for OSU's Computer Science Capstone. Our team is Michael Banks, Mark Kaiser, Jennifer Bowers, and Stephen Hunt. If you're watching this video in 2023, then you probably had a credit history in America in 2017, which means that there was at least one privately owned credit bureau managing a digital record of your private information, including your name, social security number, and address. This data was subsequently compromised by computer hackers working against Equifax between May and July of that year. As our culture becomes increasingly computerized, our information is becoming more discoverable, presenting vulnerabilities. The goal of our Capstone project is to analyze malware-based attacks emblematic of the kinds that would exploit these vulnerabilities. This can be done in two basic phases, statically and dynamically. Static analysis consists of gleaning any information of the malware outside of its execution, such as by disassembling an executable into low-level processor calls, and studying its software dependencies. Dynamic analysis revolves around studying the malware as it executes, observing how it uses system resources.
In today's world, computers are at the heart of every industry, and this heavy reliance is why confidentiality, integrity, and availability are so important. Malware is created to disrupt all of these. I'm going to walk through the analysis environment we built and configured. Then I will cover some of my favorite static and dynamic analysis tools used throughout the project. Our malware analysis environment consists of two virtual machines, a Windows XP virtual machine with analysis tools loaded, and a Remnix Linux virtual machine which comes with many analysis tools. Both are isolated with this virtual network adapter where it is isolated from the open internet and bare metal host. Finally, after configuration, a clean baseline snapshot is taken for each virtual machine. Now let's highlight some awesome tools for the static analysis phase. PE Studio, FlossFlare, and IDA. So this is PE Studio right here, which has interesting strings, MITRE attack techniques, imports, shows the libraries, imports hash, and then the binary hash itself. The next interesting one is FlossFlare, which takes strings a step further and pulls out stack strings, which are dynamically built strings at runtime. And then the last is IDA. IDA is a disassembler that allows you to inspect binary and assembly representation, and it'll pull out many interesting properties. And then thanks to FLIRT, Fast Library Identification Recognition Technology, IDA is able to recognize standard library functions. This helps the analyst better understand the assembly they're looking at. Out of the dynamic analysis tools, we've got Process Monitor, x64 Debug, Wireshark, and INetSim plus Fake DNS. And Process Monitor gives you the ability to see any registry key modifications, any registry keys that were created, new files that were created, new threads that were spawned. This allows the analyst to see if maybe persistence was created with like an auto runs registry key, or when a service is created, registry keys are created there as well, or if there's maybe a keylogger, that file will be on disk. And then next, x64 Debug, which allows you to step through a lot of applications and then look at the assembly, change behavior, such as if there's anti-sandbox techniques employed, you can flip a compare a test instruction to, instead of a jump not zero, to a jump if zero, or etc., to force that other code flow. And then here we've got Wireshark, allows you to capture network traffic, analyze, extract objects, follow TCP streams. This here is a little Python web server we put on Remnix so that we could move files back and forth for like artifacts, so we could restore the snapshot and not lose everything. And then finally, I spoke about INetSim Fake DNS, which will feed the malware whatever it wants over the network to continue to tease out additional artifacts. And then here's Ghidra, which is a decompiler, and you can see that decompilation on the far right-hand side.
The keylogger, malware sample number 1. In the static analysis of the keylogger, one of the first tasks for Michael and Jennifer was to take a hash of the malware and check to see if anyone had encountered it before using the popular website VirusTotal. This availed a threat label of Explorer Hijack /A09 UI3P. When the pair opened the malware executable in PEID, PE Explore, and Floss to observe the strings and imports listed with the executable's resources. Among the Windows functions listed were those related to manipulation of files via kernel32.dll, as well as a reference to svchost.exe. This inclusion would become understood during dynamic analysis. Mark and I carried out the dynamic portion and used primarily Process Explorer, Process Monitor, and Wireshark to observe what execution entailed. The fruit of this was the observation that the executable carried out a chain of registry and file edits that allowed it to leave an imposter svc host.exe behind in Explorer, whose function was to oversee the recording of keystrokes from the top window into a plain text file in the directory where the original executable was contained. Normally, some form of data extraction method is expected, but use of Wireshark and Netstat confirms that there was no attempt to send the logs data through the internet.
The evasive DLL, malware sample number 2. The second malware sample, Lab 5.1, called for progressively stronger static analysis skills using IDA, the interactive disassembler. The static analysis team, consisting of Mark and Stephen, discovered evidence indicating that the malware could perform critical create, read, update, and delete operations. Examination with IDA revealed multiple red flags, mainly relating to functions imported from other DLLs. Here are several examples of import functions potentially accessed by this malware. The extent of these functionalities suggested that, when coupled with a permissible executable or script, the DLL had the potential to perform complex actions such as process injection, service creation, and the ability to establish network connections. The dynamic analysis team, Michael and Jennifer, deployed an array of investigative tools to extract additional insights from the malware. Despite their comprehensive approach, the team was unable to execute the malware, perhaps due to its intended development for static analysis. Despite this, their methodical examination corroborated the static analysis team's findings and provided the team an invaluable opportunity to refine their skill sets by handling various analytical tools, which are listed on the left. Documented findings are on the right. This malware clearly has many capabilities, the most concerning of which is the ability to create a socket connection, also known as a backdoor over FTP or HTTP. Creating a backdoor is a common tactic to open a pathway for deeper unauthorized access into a system.
Denial of service exe malware sample number 3. For this sample, Jennifer and Mark performed a static analysis. They found multiple imports, as seen on the left, that suggest the ability for the malware to hijack a service and inject itself as a process, evade sandboxing, and maintain its life with persistence at restart. These are common tactics that malware uses to maintain its existence and avoid being detected. The static analysis group also found an elusive mutex, a link to a website, and some interesting clock-based functions that seem to suggest more, seen here on the right. By looking at the source assembly code, Jennifer and Mark found that the mutex is a way for the malware to make sure it does not open more than one instance of itself on a target machine, and that the clock-based functions store a date and time that the malware is allowed to run after. It was set to detonate any time after January 1st, 2100. As seen on the left, the year 2100 was stored in hexadecimal as 834. In order to get the malware to run, this value needed to be changed to the year 2023, hexadecimal 7E7. For the dynamic analysis, Michael and Stephen altered this section of assembly code, connected to the network, and detonated the malware sample to observe it in action using Wireshark. As seen on the right, the malware performed a denial of service attack by flooding the websites practicalmalwareanalysis.com and malwareanalysisbook.com with HTTP GET request packets, causing latency issues and potentially shutting down the website.
In conclusion, we've uncovered stealth intrusion methods, been challenged with sandbox evasion techniques, and carefully examined malware payloads and behaviors. That said, as we peer into the future, we understand that our work is far from complete. If time were not a constraint, our team would read the remaining chapters of our textbook, aspire to create our own malware analysis tools, delve into writing our own malware samples, explore the nuances of precompiled code, and study in detail the obfuscation techniques employed by malware developers. With rapidly growing technological advancement, artificial intelligence, machine learning, and quantum computing are set to revolutionize various sectors. Our team anticipates the emergence of self-evolving malware capable of adapting strategically to defenses it encounters. Quantum computing could enable malware to crack even the most secure of cryptographic protections. Our future commitment isn't just reactive, it's proactive. Each team member is either already working in the security field or plans to, whether it be with the FBI, offensive security, or systems administration. Our team is committed to researching, anticipating, and preparing for emerging threats as we continue to adapt and evolve to the challenges of our respective fields. While the journey ahead is challenging, we are confident in our ability to advance and respond effectively. A special thank you to our project manager, Instructor File. And thank you so much for watching.